Okay, so let's go for the second part of the radio access network subsection in this presentation. So now we are going to talk about, we are going to use as an example of functional to highlight functional splits in the radio access network, the Flex 5G Ware project, in which CTTC is currently working. So this project is an H2020 project that is expected to finish at the end of June. And I will provide and use this project as an example for you to understand what a RAM functional split is and what kind of KPIs can be optimized with this kind of functional splits in the radio access network. So Flex 5G Ware, its main goal is to enable flexibility in the radio access network by devising different RAN functional splits. Every RAN functional split can target different KPIs. So, for instance, if we want to minimize the energy consumption at the edge of the network, we may be interested in moving the whole NFV stack, but the remote radio head, from the edge and move it to a cloud. So note that if we do that, we are reducing the energy consumption at the edge at the expenses of incrementing the energy consumption in the cloud. Okay? Some more goals of this project. So this project also try to improve other parameters such as capacity. So in function of the latencies allowed between the different functional split and the infrastructure you have to allow these latencies, you may be able also to improve or worsen the capacity depending on your requirements. So here, just for the sake of following the concept I mentioned in the previous part of the presentation about the blurring, the barriers between the RAN and the core, and the backhaul and the fronthaul. So here I show you some of potential functional splits that can be implemented. Some of them are being currently implemented and finished the implementation in the Flex 5G Ware project. So for instance, there are, at the beginning of the project, there were like 3 different, let's say, places where you can implement RAM functions. So first, you can implement things in the edge. You can implement RAM functions in the edge as software. Another option is to implement these RAM functions as hardware in an FPGA. And another function is to implement these functions far from the edge in a cloud data center. This does not preclude that you can have even also in a cloud data center an FPGA to implement some function in hardware also. So let's fix our attention, for instance, in the cloud stack RAM functional split. So this one is specifying that from the MAC layer up to the S1 interface, this part of the NFV stack is implemented in a cloud data center. and DPC, represented by these 4 boxes here, the serving gateway, the MME, the HSS, and the packet gateway, is implemented in the cloud, far from the user, far from the antenna. Close to the antenna, it's only implemented the baseband part, the phi baseband part, in hardware, using VHDL. Another potential functional split is that attempts to allow the dynamic hardware-software partitioning of physical functions. This one here. So this one is proposing to implement some functions of the physical baseband in an FPGA, so in hardware, some other functions also close to the edge in a generic purpose processor, so in the edge, but in software, we implement some of these physical functions, and from the MAC layer up to the S1 interface, we implement all the functions of the NFV in the cloud, as well as the EPC. Of course, there are more potential splits. For instance, typical one for mobile edge computing could be this one, having all the LTE stack and the EPC in the edge. This is what we refer here as network in a box. Basically, you have in the antenna the baseband processing implemented in the same within the same node with an FPGA, and in software with a generic purpose processor, you implement the rest of the NFV stack and the EPC, but everything in the same node. So this is basically some of the stuff I was mentioning. So we can implement things in hardware, we can implement things in software. In this project, for the hardware, we used an FPGA and implement phi baseband processing with, yes?
I just wanted to ask, so you're basically talking about making it a flatter architecture, so bringing the functionalities of the core network to the edge.
Yes. This is one of the options.
These functions are from the RAM, not for the core.
Yeah, but of course the EPC is also there, but it's not splitted, the EPC. Here we talk about functional splits for the RAM only. So the EPC is there because, you know, to test things you have to implement an EPC, but it's running in a single as a single process without the coupling functions of the EPC. Okay.
But we are putting all the functions at the edge.
It's a possibility. Yeah.
So won't it make the edge nodes, more costly and bigger because we are putting more resources into it?
Yes. So a typical use case for doing that is when you have a mobile user subscriber that wants to decrease latency at the cost of increasing computational power in the edge, as you mentioned. So this project is about optimizing one KPI or another KPI. It's not only about optimizing energy power at the edge, the energy consumption at the edge. So in this case you mentioned, at the expenses of increasing the energy consumption in the edge, you decrease a lot latency. This could be very interesting, for instance, for augmented reality applications, virtual reality, or online gaming. So, well, It depends on what the customer needs, you know.
There is a trade-off.
Yeah. Yeah, when you optimize one metric, you may worsen another metric. You can have it all. Okay, so as I was mentioned, you can implement things in hardware using an FPGA, and in software, in this project, we use the Lena open source LTE and EPC network simulator and emulator. This implements, Lena implements an LTE-like stack and an LTE-like EPC that can run in simulation mode and also in emulation mode. In emulation mode basically means that you can run with certain modifications in the Lena code, with a lot of modifications in the Lena code, you can run things and interact with the with a real testbed. So you can have an NFV that interacts with this physical FPGA and sends over the air LTE-like compliant messages. So some of the research and design challenges of this partition and of RAM functions and functional splits is to seek for the optimization on some KPIs at the expenses of potentially degrade some other KPI. And a very interesting thing is that some of the functional splits could be potentially reconfigured. Okay, within this project, correct me, Marco, if I'm not wrong. We are developing platforms that implement functional splits on a static way, so we cannot change from a functional split to another functional split dynamically. This will be a step beyond. So this is the use cases. So the use cases of the project. So the dense urban society, for instance, implementing Cloud Run in a dense urban scenario formed by small cells could be a potential use case. The idea is to make some cost-efficient, high capacity and energy efficient platforms, and the expected benefits are improving some KPIs depending on your scenario. So let's take a look at some of the platforms. So this is some of the platforms that we were talking before, some of the potential functional split. This is called the cloud stack. So basically, all the NFV stack from layer 2 to above and DPC runs in the cloud, as you can see with Lena, in a separate process. And what we have in the edge is this box here, which endows the RF front end. And in the FPGA area, we have the layer 1 stack. Of course, to communicate the layer 1 stack to the layer 2 stack of the NFV, we need to develop a proper API between the baseband part and the cloud part. This is what this box here is doing, using a generic purpose processor. Using in this dual ARM generic purpose processor, we are running a Linux operating system that is implementing this API that communicates through a backhaul channel to the layer 2 stack of the NFV. So these are more details of this physical partition. I will pass them through to fix our attention. Let's fix our attention now to a modification of cloud stack, the cloud stack partition. But in this case, instead of having the edge node, so the NFV in the cloud, we have it in an edge intermediate node. In which case we can, it could be interesting to do this. Well, in the case where at the edge we are not that interested on minimizing the energy consumption. We are more interested in minimizing energy consumption here, and where the latency between the cloud and the part of the edge is not, does not allow to interact the layer 1 stack to the layer 2 stack of the NFV. So if the latency, so there are latency requirements. So if the latency does not allow to do this functional split in the cloud, we can do it in the edge at the expenses of increasing energy consumption in the edge. So basically, as you can imagine, it all depends on the kind of backhaul channel that you have, the KPI that you want to improve, and the scenario that you definitely the scenario that you have to make one functional split or another. So another example is CRAN. So basically in CRAN we have in the edge part only the RF part, the remote radio head, and through CPRI we can transfer the front haul traffic generated by this remote radio head to the FPGA that in this case is hosted by the cloud. So here, in this case, we have a very good channel that allows us to do this kind of transmission using CPRI protocol. So delay requirements can be satisfied by this high capacity, low latency channel. And we can minimize to the maximum the energy consumption at the edge, because there's only the RF part here. And then another example will be that intends to move functions that are run in the FPGA area to the generic purpose processor area. So depending on the needs and the specific scenario, dynamically some functions that run here in the FPGA area can be moved up to be implemented in software, and the functions that run in software can at some point be interesting to be run in the hardware. This is for the layer 1 level. This is just an example of kind of a split that can be done more with by adding a little of dynamicity to the mix. Yeah.
When you are implementing, for example, a layer 1 stack in one processor, you have a different implementation when you are implementing in, for example, in general purpose processor.
Yeah.
So
yeah, it's totally different.
Completely.
It's totally orthogonal, right? The requirements.
If you want to change from one configuration to another, you have to be.
You need to be a very huge processor here to be able to do that. And this is one of the configurations that are not being implemented in the project. It's just an example because of the dynamicity. So this is it's more a long-term thing, that something that is going to be delivered by the end of the project. Okay, so I just showed you some examples, and what will be the next step after we have some of these functional splits implemented? It will be very nice to have, within the context of another project, to have a dynamic, reconfigurable RAM functional splits. So we can, for instance, go from the cloud stack to the network in a box paradigm dynamically, according to the needs of the specific scenario. Okay, so these are some details of the RAM virtualization testbed. So we use Lena for the part related to the software, from layer 2 up to the application layer, for both the UE, the NFV, and the EPC. And for the physical part, we use FPGAs from this what is called the Jedomis testbed of CTTC. So the good thing about Lena, as I mentioned here, is that with some effort, you can, and developing the proper APIs, you can achieve to talk the simulator Lena stack to the real physical FPGA. Or with some effort, you can make any kind of NS3 module to talk through a net device to a Linux interface by means of this emulation mode, which is basically based on raw sockets that implements the proper APIs between the devices, the physical devices and the emulated devices. Okay, so this is a picture of what we would like to have in the long term. So basically, imagine that we have a RAM functional split. We have the physical part here within this testbed. We have an edge data center here, where, for instance, we can run the LTE stack. We would like to use as front hole of the RAM partition a millimeter wave and YGIG based mesh backhaul for the front hole segment. Even make the front hole traffic pass it through a multi-layer optical network, and finally arrive to the other end of the RAN split in a core data center. So right now, in Flex 5G, what we have here is just a 10 gigabit Ethernet cable from the Jedomis testbed to the edge data center, to a edge or core data center. But in the future, we would like to replace this by a hybrid, wireless, and multi-layer optical front hole and back hole. Okay, so this is just a recap of the main concepts we have studied here. So soft RAM for the decoupling the LTE control plane from the LTE data plane, radio visor for enabling multiple slices in this soft-RAN architecture, and finally, Flex 5G. We have studied RAN functional splits by studying a project, by summarizing what we have been doing in this Flex 5G web project that aims to deliver 5G hardware software reconfigurable platforms. Okay, so maybe now we can go to the part of this talk that goes to the application of SDN and NFV to the Evolved Packet Core. So let's start with Softsell. So basically, Softsell, if we take a look at the typical architecture of a mobile network, and now we fix our attention to the part related to the core, we have that we can think that the packet data network gateway makes a lot of things, has a lot of tasks to do. So it has to do a lot of processing. So some of this processing comes from doing traffic classification, establishing fine-grained policies for the customers, enable billing, accounting. So the problem is that these boxes are closed and perform a lot of functions. They are doing a lot of things. And you usually don't scale up and down these kind of functions because the hardware is quite rigid. The hardware that is currently deployed in the Evolved Packet Core networks. Okay, so this is what I was just mentioning. So the problem of this is that this is not flexible. We cannot, if we want to add, for instance, a new functionality, and this is related with the concept of SDN, if we want to add innovation to this box, to this packet data network gateway, we cannot do that with current deployments because it's a black box that nobody touches. You plug in, and you expect it to work. You have some specifications, some data sheets, but do not touch it. Do not program it. You cannot, practically, you can configure some generic things, but don't expect it to be flexible. Okay, so these are some characteristics of the core network. So basically, as I told before, every customer has their needs. Every customer will pay more or less depending on the kind of prioritization you want to enforce to this user. And there are a lot of policies. In addition to this, in a mobile network, if you want to establish any kind of communication pattern, you have to traverse this PDN gateway. If you want, for instance, to talk between two UEs that are here and here, you will not do like this. You will not go to the base station and come back. You will have to reach the EPC and come back, unless you do some local breakout, which is currently not the rule in actual deployments. So basically, you start here. I want to get a web page from my mobile phone, I have to go here. I have to call to this other user, I have to go here. I have to download a video from the internet, I have to go here. So you don't do like this. There is no local breakout, usually. So this is what we mentioned about these characteristics, which is the north-south traffic patterns, this kind of hierarchy that you have to go at the end to the PDN gateway. Okay, so let's see what Softsell proposes. So we have our mobile network, we have the radio access network, we have the internet, which is our exit point from this mobile network. What Softsell proposes is to first convert this circuit switching EPC-based circuit switching EPC network to a packet switching EPC. This implies removing all the tunneling that starts here and ends here in current deployments, GTP tunneling, and move out all this functionality from the gateway of the EPC to these access switches and these intermediate switches. So instead of having one expensive box, we have a lot of simple boxes. So we put a controller that controls this switch here, and all these intermediate switch, the middle boxes that can be performing any network function interesting for the core network, and this gateway to the internet. It's not anymore a PDN gateway. It's just a simple switch. It's a white box that this controller programs. This doesn't change the radio access network. The NFV stack is unmodified. Okay. So here you can see how this, what are the characteristics of this solution. So we have an asymmetric edge, which basically means that usually here we have a lot of capacity. Here we have less capacity. Okay. Here we have to deal in current deployment with a lot of flows, or in the order, for instance, if we assume that each user has 10 flows, this box here has to aggregate all the users that are connected to these boxes here. So if we have 1,000 users here, we'll have on the order of millions of users here. If these users have to deal with or are initiating 10 connections, this box here, with no modifications, and if it were a PDN gateway, will have to deal with 10 million flows. Okay? So this means a lot of processing. On the contrary, here, these boxes have to deal with 10,000 flows if one user has to deal with 10 flows. This has implications in terms of bandwidth. So here we're talking about some terabits. Here we have talking about a few gigabits per second. Some assumption this proposal is doing is that the traffic usually is initiated from the UEs. So if I want to get a web page, I make an HTTP GET from my mobile phone. Or if I want to download a video, I will do an HTTP GET, and the video will download. So the assumption here is that usually is the UE initiating the connection. So what Softsell proposes is to start packet classification at the access edge. So basically, instead of performing packet classification and fine-grained service policies in the edge, we do it in the core. Sorry, instead of doing it in the core, we do it in the access switch. And then we generate rules for switches that are in the middle in order to reach the gateway core. The thing is that this is feasible because with the current assumptions of users attached to each one of the base stations, ternary content addressable memory switches, we have a node memory to handle this kind of flow table entries. So the thing is also that we are including a controller here. We are including a controller which have to deal with a lot of requests. So we do not want to overload the SDN controller that has to manage the EPC. So what Softsell proposes in order to have a scalable system design? First is classifying the traffic flows at the access edge. The access edge is here. Here, for every user initiating a connection, the switch will assign a policy tag to each kind of connection that demands a certain QoS requirements. So what happens is that when a UE attaches to the network, the switch sends to the controller the UE identifier. So now we don't have GTP tunnels, okay? So the packet that is sent by the UE here is not tunneled in a GTP S1 tunnel. There will be an IP rewriting of the IP source address here, okay? But let's go step by step. So the UE registers here in the SDN controller, and the SDN controller installs in this switch some policies for this UE according to the mobile subscriber attributes that this switch has sent to this controller in order to perform a posteriori traffic classification when the UE initiates TCP connections. Okay? So I will explain it in more detail later. So basically, by achieving this, what we have is that some of the tasks that the controller has to answer to are controlled by this local agent. So when the UE subscribes to this SDN controller put here some policies for this UE, for all the flows that this UE has to deal with. When the UE initiates a connection, a TCP connection of any kind, instead of asking the controller, this local agent will apply a traffic classification policy for the just initiated UE connection. So let's see if everyone understands this. So what Softsell is trying to avoid is to overload this SDN controller. Okay? So that when a UE initiates a TCP connection, you don't have to ask the SDN controller. It's already, the policies are already installed here. So basically, if the policy can say something like, okay, If the destination port is TCP and is port 80, which means web traffic, send to this switch here and put the policy tag number 3. If it's port 2020, assign the policy tag 4 and go from other switch, go to the edge through another switch. Okay, but without asking the SDN controller. Because a UE is one registration, once it has registered, never will ask again another thing. However, if we don't have this local agent here, every time a UE initiates a connection, it will have to ask the SDN controller. And we don't want that, to not overload the SDN controller. In addition to this, Softsell proposes to enforce policy consistency through mobility, under mobility. Basically, we want to force that even though you may detach from this base station and go to this base station, the set of traversed middle boxes during a handoff are preserved. This means that if, for instance, I have a UE here connected to this one, and there's a stateful firewall here keeping the state of the TCP connection, and the UE moves here, traffic has still to go through the same set of middle boxes, including the stateful firewall. Otherwise, the TCP connection will suffer from problems. And finally, another thing that Softsell proposes is to aggregate flow rules in the intermediate switches from the access to the gateway edge. So Softsell avoids the unlimited increase of flow entries by aggregating flow rules. How does it do that? By assigning location-based IP addresses to the traffic that the UEs generate, rewriting at the access switch the IP source address. So let's take a look at that. What kind of tags can we have in this multi-dimensional aggregation? Policy tag, the base station ID, and the user ID. The policy tag is used to aggregate flows that share a common policy. The base station ID aggregates flows that come from the same base station ID. And the user ID can aggregate flows. It's a tag that can aggregate flow entries that go to the same user ID. Remember that the same user can have in parallel several TCP connections. So the idea is to exploit the location of these UEs to assign a hierarchy in the IP addresses assigned to these UEs when they attach to a base station. So let's put some examples here. What do I mean by location-based hierarchical IP addresses? So we have 4 base stations here. Each one has a prefix, okay? 10.0/16, 10.1/16, 10.2, and 10.3. These are the kind of addresses that the UEs, the traffic originated from the UEs, will have in the IP source when they traverse the first access switch. Okay? So the UE has 2 addresses in this case. One address for identification, for identifying themselves, another address for identifying their respective location in this hierarchy composed by these different base stations. So basically, this is a UE. This is the IP address that identifies the UE. And we can see when the UE initiates a TCP connection, the IP address is rewritten. The IP source address is rewritten from 192.168 network to a 10.1 network. This 10.1 identifies the base station ID to which the UE is attached, and the 0.7 is a suffix that identifies the location of this ID. Okay? This UE ID is unique, of course, within the base station ID. So let's put an example here. Imagine that we have two base stations, and we want, instead of having a rule for each one of the UEs, we want to aggregate for in this switch the rules for all the base for all the traffic that goes to the UEs that go to base station 1 and all the traffic that goes to the UEs in base station 2. So it's as easy as putting a match here from the prefix announced by each one of the base stations. So if the prefix matches the base station 1, we forward to base station 1. If the prefix matches to base station 2, we go to base station 2. Remember that these matches and actions are programmed by the SDN controller of what Softsell proposes. Same here, we can increase the level of aggregation as we move forward to the internet. If we assume this hierarchical deployment, the gateway to the internet with only one rule can discriminate between the traffic that goes to base station 1 and base station 2 and the traffic that goes to base station 3 and base station 4, which are not depicted here because of the space, but you can see that there will be 2 more base stations in this part of the network that will be achieved through this path here. So it's about aggregating forwarding rules in the switches. Okay. So this is kind of the job that the PDN gateway is doing, and also note that there is no tunneling here. There is IP source rewriting here, and then when packets come from the internet to here, there is a rewriting in terms of IP destination. But there is no GTP tunneling. Another example here. So now we want to discriminate between what traffic goes, what video traffic goes to transcoder 1, what video traffic goes to transcoder 2. These are middle boxes that are usually embedded or can be embedded in a PDN gateway, on a core network. So, for instance, here we want to implement a policy that determines that traffic initiated from UEs attached to base station 1 or base station 2 have to pass through transcoder 1 before leaving to the internet, and traffic originated from UEs from base station 3 and base station 4 go to this middle box here. What we do is to put this set of rules in switch 3, which basically, the first match is we match with Tack 1 in switch 3. Tack 1 means transcoder 1. The IP address means base station 1 or base station 2 prefixes, aggregates the two, and it says go to transcoder 1, and then go back to here. The same for traffic initiated from base station 3 and base station 4. Here we specify a match with tag 1, which means in this case video. And here with this match, we enforce that traffic generated by UEs attached to base station 3 and base station 4 go to transcoder 2. Okay, so other things that Softsell can do. So basically, Softsell tries to enforce policy consistency, which means traversing the same set of middle boxes no matter the location of the UE for ongoing flows. For instance, let's try to see an example. We have this UE. This is the IP that identifies this UE. This is the IP that identifies the location of this UE, which is the IP that is rewritten here in the NFV. Sorry, not in the NFV, in the access switch for all packets that are for all traffic that is originated from this UE. There is a flow here going straight to this UE. And then there's a handoff. The ongoing flow is still ongoing. It preserves this IP address as identifier of the UE, but there will be a new assignment here. What happens with this old flow is that Softsell enforces, instead of recalculating the path to go from here, from the ongoing flow, it still passes through this firewall, which keeps the state of the ongoing flow. And then, when the traffic arrives, the old switch to which this UE was attached, you redirect the traffic to the new location of the UE. All this to enforce that an old flow traverses the same set of middle boxes as before the handoff of this UE happened. So when the UE attaches to this other base station, this is the new identifier of the location of the UE. And if a new flow arrives, instead of being the traffic rewritten to the old IP address, it's rewritten to this other IP address. However, the old flow will still go with the old IP address, with the old location IP address. Okay, so when I say about encoding policies, when I mention about encoding policies, encoding location-based IP addresses, where do we put in the IP header all these matches? Well, so the base station ID is encoded in the prefix of the source IP addresses for packets that are in the uplink connection from the UE to the internet, and in the suffix of the source IP addresses to identify the location-based UE identifier. And the policy tag is encoded in the source port of the IP addresses. And in the return path, when packets go from the internet to the UEs, instead of using the source IP and the source port, we use the destination IP and the destination port. The good thing about this kind of encoding is that current versions of OpenFlow implementations allow the matching of this kind of fields. We can, in OpenFlow 1.3, which is the current implemented version of virtual, almost implemented in all virtual switches, we can have matches by policy tag encoded in the source port and matches by source IP and or destination IP or destination port by using OpenFlow 1.3. Okay, so this is the summary. So it's only 13 minutes. So let's try to go faster now. Let's take a look also about the control plane load. In this case, it's always something to take a look to when you have an SDN solution. So here the problem is that if you don't put here a local agent, the local agent I was planning before, there will be a lot of frequent switch updates. And as you move to the internet, the number of the level of aggregation of flow rules decrease. So basically, it's not a big issue to have the length of the rules in the intermediate switch and the gateway core switch. So well, this is the summary of this solution. It's about exploiting multi-stage tables. It's about replacing commodity switches by BDN gateways, and to achieve in order to achieve scalability and deal with scalability issues in the EPC. Yeah. Yeah.
This architecture.
Softsell?
Yeah, Softsell. How can this architecture be compatible with legacy? So we need some in the SDN controller. We need to implement.
Well, it will be something that, as usual, is not compatible with legacy equipment and the legacy mobile network layer. So it will have to be developed from scratch.
So, for example, there is no chance to have, for example,
a combination.
Yeah, kind of. So if you're implementing functions in the SDN controller that are the function.
Well, you can.
Gateway,
The problem.
then you map all these architectures
Yeah.
with legacy procedures and messages. Maybe you have the chance to.
Well, I think that as long as you, if we are thinking about a lab and a research, yeah, possible is possible. Now that I think again on this, but you note that you will need to have a legacy PC here, and somehow this there should be some rules implemented in the access switch that say, okay, don't touch the GTP tunnel, right? So.
Or enforce the forwarding policy based on the messages that are passing through the bigger setup or mobility management.
Mm-hmm.
And there is no GTP tunnel that you have to map the information there on all these forwarding policies that you mentioned.
Yeah, maybe we can have something like a default rule for legacy traffic that instead of going through these white boxes, we go through the legacy EPC.
Anyway,
Yeah,
the guys proposing these are not touching.
yeah, they are not touching the problem. But well, it's nice to think about it, right? Yeah.
And so, does that make it easier for multi-homing or multicasting? Because if a device is connected to two base stations, then
Well, if you refer to multi-homing, so the way I understand multi-homing is that a UE, in addition to having an LTE connection, may have another kind of connection to reach the internet, right? It can be a satellite ground station or a Wi-Fi connection. But the IP addresses that I mentioned here are not touching, are not assuming multi-interface capabilities in the UEs. They're assuming just one interface with several IP addresses, one for identification purposes of the UE, and another one to encode the location of the, and this is, let's say, orthogonal to the multi-homing problem. In the multi-homing, you have an IP address for each interface and an identifier for the UE.
standardize, the location independent name of the device itself across the, access technologies, and so the IP address given by a particular access technology like LTE, that becomes a location dependent name address, and the device is identified by its own ID.
Mm-hmm.
So both the access points, they know to what it is transmitting.
I think what you are saying is something related to mobile IP, right? That you have. Okay, so in mobile IP you have an identifier, and in fact it's related with this kind of solution. So if you take a look at the ITF draft of mobile IP, it will explain that UEs can have they have an identifier of the terminal or the UE and a location dependent address, which is assigned by the. In that case, it was about Wi-Fi access points. I think they changed they assign an IP address in function of the access point to which the client is attached. I think you can take a look at this because this kind of assignments and location-dependent addresses and identifier IP addresses are explained there.
There was some standardization.
Yeah. See, if you are looking for a standardization, I think this is the place to go. Mobile IP. What do you think? You know more than this about this, right? Yeah.
There are different procedures there, so you can, if you are interested.
Okay, so we have 20 minutes, so I'm gonna skip. What I'm gonna do is to skip this one. I'm gonna go quickly with this one, and then I will do my best with this one. Okay?
You can skip it or be very quick in
NM court. Okay. Okay, we can do that. Yeah, because it's like 20 minutes. Yeah. I will be quick with MCORT. So MCORT stands for Mobile Central Office Re-architected as a Data Center. It was an initiative initiated by the Open Networking Lab and the Linux Foundation last year, in summer last year, in July. And the main idea is something related to what we were discussing in the first part of this talk, which is about merging the best of SDN, NFV, and cloud, and open innovation to create innovative services on top of a physical shared infrastructure. So this is the ecosystem. So we have, you can find here vendors, operators, data center providers. We have NEC, which is everywhere. So okay. So some of them. So also these guys are the creators of an SDN controller called ONOS. So basically, all this initiative believes a lot in what I was mentioning before. So democratization of the democratization of the software, open APIs, avoid the vendor lock-in, and all the code that they develop is you can find on their web page. They are making releases of ONOS and their orchestrators every 6 months, I think. So, if you are starting and you want to get familiar with SDN and NFV and so on, and you have to do experimental work, this is a good place to go. So, basically, the main idea behind the mobile core, well, let's explain just very briefly what is core. So basically, central office is at the very edge of the telecom, and what happens is that there are a lot. On the one hand, there are a large number of central offices. You can find, secondly, you can find equipment that has 5 years, 10 years, 15 years, and it still it works. So this means that when someone wants to add something, be careful. It may not be compatible with all equipment, and so it's a difficult thing. So, and the third thing is that there's a huge increase of capex and opex by acquiring these black boxes. So what they propose is to, okay, let's exploit these 3 technologies to commoditize the infrastructure in the central offices. Okay, so what they are trying to do is to apply to the telco what was applied to the data centers 10 years ago, basically. Well, 10 years, 10 years. So basically, let's apply the leaf-spine fabric, so east-west communication between the different white boxes, and on top of that, let's instantiate with a control plane and an orchestrator all the service function chain or slices of whatever you want to call it, composed by different virtual network functions, virtual computing functions, and virtual storage functions. So basically, this represents the access. So here you can find mobile subscribers, residential subscribers, enterprise subscribers, and here you have the core network, the backbone. So okay, I went through this. So the problem for the problem from the case of mobile core, which deals with the mobile subscriber, is the part of core that deals with the mobile subscriber, is that operators are slow in their revenue. It's the average revenue per user is declining, and basically these are the operator challenges. I mentioned most of them before. So it's slow. Creating innovative service is a huge pain in the ass for black boxes. It's difficult to achieve customized service for every user. So we need fine-grained policies. It's not the best effort for everyone anymore. And also, what Mobile Core wants is to make the most of the resources in the central office. Okay, so if you add to the mix agility and costs for efficient deployment, this is some of the 5G capabilities that this initiative is trying to exploit. So yeah, I already mentioned, make the most of the resources, customize services, and enable open innovation. So they are advocating for disaggregating the RAN and the EPC. It means control plane decoupled from the data plane on the one hand, and virtualize the control plane functions as well as the data plane functions. This is what we mean by virtualizing and disaggregating. So very quick. So this is the kind of services that MCore is tackling. So mobile edge services, disaggregation and virtualization of the RAN and the EPC. There are a number of factors involved in this. Network slicing, open interfaces, programmable data plane. So this is the rigid and hierarchical infrastructure of current mobile networks, and we want to change that with SDN, NFV, and cloud to go for a more flexible service composition of all the mobile network functions: BBUs, serving gateways, PDN gateways. So the main idea here is that every one of these functions have to be offered to the clients as a service, okay? And you have to instantiate, and the way to have this flexible service composition is to commoditize the physical substrate underneath. So well, this is the target architecture. So if we take a look to mobile edge services, the main enablers for this are IoT critical applications. It's important to have some kind of proximity-based QoS so that end users that demand latency in the order of a few milliseconds can achieve that. One way to do it is to enable local services in the edge. For instance, as I mentioned, for IoT critical applications, for augmented reality, for virtual reality. So delay is a bigger problem that mobile core is trying to tackle. So it's not anymore about 50 milliseconds. It's about the experience. It's about getting even 2 or 3 milliseconds of latency to have a good really experience with virtual reality, for instance. So this is the architecture of MCore. So it basically, I put it in the part of the core network, but it basically deals on with the very three segments of the network, because of this blurring of network functions from the RAN and DPC and to the backhaul and the fronthaul. So these are some of the expansions that MCore is facing for 5G. So in addition to virtualization and disaggregation, they are also very motivated to break this connection-oriented, based on GTP tunnels, mobile network layer. They want to make it more like IP, so not connection-oriented. So one of the things they're saying is that, well, now with vertical industries, mobility may not be an issue for certain vertical industries anymore. For instance, if you have, instead of mobile users with their mobile phones, you have an IoT network. This is static. So maybe you don't need tunnels anymore to deal with mobility, as the mobile network layer is doing right now for all the users. So they are struggling with this kind of things. So let's talk a little about the software. So they say this is a pod. A pod, you can say we can define a pod as it's like a proof of delivery. It's like a set of racks and switches and servers that have some software and are working, and you have to manage and orchestrate this. So basically, what they say is that, okay, in some data modeling language, such as Django or Tosca, you can specify policies. There is a parent controller that will offer a RESTful API through a highly declarative language, and will translate these high-level policies from the mobile networks or the vertical industries to program each one of the physical hardware elements within the pod. The pod is, you can think on it as a rack of servers with the agents installed, so something that has to be managed, okay, an instantiation. So if we take a look at the pod, we can see what it's composed of: service function chain or slices that are controlled and that are controlled by a specific orchestrator, and on top of that there is an orchestrator that is defining, similar to what I explained before of the ETSI NFV. This is similar to the NFV orchestrator. It's the one that allocates the service function graphs that each one of the operators or clients are specifying. So the main idea is that everything is a service. So the BBU is a service, the MME is a service, the serving gateway is a service, CDN is a service. Okay, and we have a few minutes to talk about the backhaul and the fronthaul segment. Okay, so far we have discussed a lot about the RAN and DPC, but not that much about the transport network that interconnects all these mobile network elements. So I have said that we need RAN sharing. We need to share the resources. There are different actors involved. We can have RAN sharing, such as I explained before with radio visor. So two mobile virtual network operators can share a physical white box that can instantiate several virtual NFV instances. And on top of that, we need to manage this virtualized transport network, which can have many tenants with a low cost. So we are involved in a H2020 project that is going to finish in December of this year, which basically deals with this kind of issues. Deals with this transport network that we need to carry fronthaul and backhaul traffic. Fronthaul to carry traffic from the functional splits, for the RAN functional splits, and backhaul traffic that carries traffic that is going from the RAN to DPC. So the main idea behind this project is that it proposes to use the same transport network to carry both kinds of traffics. So it has several implications. Basically, the implication that it has is that it has to define a framing format able to carry both kinds of traffics, both backhaul and fronthaul traffic, which is called the cross-haul common frame, which is this entity here. We have also to design and develop switches and routers that are able to forward fronthaul and backhaul traffic. This is what is called the XFEs, which stand for cross-hole forwarding elements. And we need, for the RAM functional splits, we need computing nodes that are able to host the DBUs, for instance, right? So these are the cross-hole processing units. On top of that, we need to control all these data plane elements. How this is done? This is done with the cross-hole control infrastructure, which is an SDN enabled and NFV enabled control and management orchestrator that offers several services and offers a northbound to different applications, which is the last point here. We need applications for energy management. We need applications, for instance, in this project, we have applications for TV broadcasting, resource management, more applications also on the CDNs. So, well, this is the system architecture. So, as I mentioned before, we have the XCI, which is the main building block here in the cross-hole architecture that basically deals with the control, the management and orchestration of network functions and computing and storage functions by means of the SDN controller, storage controller, and computing controller. It follows the architecture of the ETSI. So it has the NFV orchestrator, the VNF managers, and the virtual infrastructure manager, and offers a northbound interface to each one of the novel applications. We have applications for mobile edge computing, for CDN services, for energy management, and here there are all the data plane elements that I mentioned before, the cross-hole forwarding element, there are legacy switching elements. There are cross-hole processing units. It's also important to note that the project deals with the transport network to carry backhaul and fronthaul traffic within the same transport network. But in order to do that, there has to be a tight interaction with both the access management and orchestration framework and the core management and orchestration framework. This is done and proposed in the system architecture to be done by using east and west interfaces that, based on REST protocol, can exchange information about the status on each of the network segments and enforce the proper configuration in both the access, the transport, and the core. So just would like to take a look what we are doing in this project, as we are the partner that are leading the experimental proof of concept. So CTTC is the partner that is leading the experimental proof of concept of this project. So one of the demos we are doing in this project, and we are expected to deliver by the end of this year, is to perform hierarchical SDN orchestration. What do I mean by that? Previously, I have only showed that each solution just has one controller. But no, you can have 20 controllers if you want. Each one managing its own domain. So basically, we are proposing at the data plane level a millimeter wave transport segment that in its turn it's connected to a multi-layer optical network that is composed by 3 domains: the packet network domain, the GMPLS domain, which is these are the optical network that configures its lambdas and so on, and another packet network domain. So each one of the different technological domains, this one is based on fiber, here we have Ethernet, here we have Ethernet. Each one of the domains is managed by its own SDN controller, okay? And functions that have to be performed locally are delegated to the SDN controller closer to the domain. However, when you want to do end-to-end orchestration, for instance, by end-to-end orchestration, I mean establish something as simple as establishing a connection between a node that is on one of the edges of the domain of the three domains, and a server that is on the core. So in the other part of the transport segment, you have to go up to configure the end-to-end path to the orchestrator that has the abstracted view of the 4 domains here. Okay, so you cannot do it by configuring only the controllers on the low layers that are located at the lowest layers. You have to move the information up to the highest controller in the hierarchy, the parent controller here, which is called parent app node, and so that the flow rules between each one of the domains are established. Okay, so there's a delegation of tasks here. Some of the controllers are doing some local stuff. Some of the controllers are doing some end-to-end domain stuff. Okay? So the kind of things that we are doing is to send backhaul and fronthaul traffic over this wireless Ethernet optical network. I want to put an example of things that Crosshaul is doing at the application layer. So we are working on an energy management application. I think it's related to this, right? A lot. So basically, the nice thing and the novelty, what I found more interesting here, is that this SDN application that deals with energy efficiency is not only dealing with network resources, but with computing resources. So basically, this application is continually monitoring the network status and the computing status, and the kind of actions that this application can enforce in the data plane are within the style of, okay, let's switch on and off this link, this network link, but also let's move this virtual machine from this place to this other place because it will allow me to switch off this server. Okay? So it's not only about network resources, but also computing resources to be energy efficient in terms of computing resources. Okay, so sorry because I went too fast, but we didn't have time. But with this, I conclude this talk. So if you have any questions, or maybe not because of time, so I'll be trying to ask. Yeah, maybe it's better, right? Yeah, we have 5 minutes past. Yeah. Okay.
Any questions?